So, okay. So it's my great pleasure to introduce Professor Subir Sachdev from Harvard University. He is currently a Herschel Smith Professor of Physics at Harvard. He has been there for almost 20 years. Before that, he was at Yale University for 18 years. He's a very well-known quantum theoretical condensed matter physicist. He made a lot of contributions to quantum materials, quantum statistical mechanics, and you will also hear about the connection to black hole today. For example, he's a member of National Academy of Science in US. He's also a fellow of American Academy of Arts and Sciences. He's a fellow of Royal Society of UK. He received the last Onsager Prize from American Physical Society. He's also received the Dirac Medal from International Center for Theoretical Physics, just to name a few awards that he received. He was actually a Welsh lecturer for us in 2021, but because of the pandemic, he couldn't come in person, but he delivered a beautiful Zoom lecture. So, and one of the things that we use quite often these days is the theoretical model called Sachdev Kitaya model. We call it SOIK model. And this is a model that connects superconductivity, black holes, and strange metals, and a lot of interesting things going on in quantum condensed matter. So I'd like to welcome Subir.
Okay. Well, thank you very much, Youngbaek. It's great to be back here at Toronto, a place I visited a lot, and especially enjoyed all the discussions today with people in condensed matter theory and condensed matter experiments and so on. Right. So as Youngbaek has mentioned, this lecture is about many topics in physics. And one common theme that I've chosen for this talk is quantum entanglement itself, and how quantum entanglement has gone from being a sidelight only of interest to philosophers of science to something that's really central to many of the developments in modern physics. That's the main message I want to get across today. All right. So I'm going to set at least the first half of my talk. I'm going to give somewhat of a quasi-historical discussion, introducing many of the ideas that I will use to talk about more recent work. And first of them being quantum entanglement itself. Now, you might be surprised to see that quantum entanglement appeared in 1865, although quantum mechanics were not discovered till 1920-something. But you'll see in a minute why I'm saying that. And there's also basic ideas on statistical mechanics, superconductivity, and black holes that date back to the early 19th century, which connect to modern developments, which I will begin by reviewing. So why am I saying that quantum entanglement started in 1865? Well, that's when Kekulé, a chemist in Germany, came up with the structure of benzene. So by that time, I mean, people knew that benzene was made up of 6 carbon atoms and 6 hydrogen atoms. And they knew a little bit about bonding and covalent bonding, although not understanding its quantum nature, of course. And this posed a problem on the structure of benzene because each carbon atom can have only one double bond, which is here represented by this ellipse. And so if you want to arrange them in some symmetrical manner, you could, for example, choose this configuration or this one. And if either of these happen, you'd get a distorted structure. It wouldn't be a perfect hexagon anymore. So Kekulé came up with the brilliant idea of what he called resonance, that in fact it's both. It's both this structure and the other structure. And according to Wikipedia, he said they discovered the ring shape during a daydream of a snake seizing its own tail. Anyway, so today we would say, well, what Kekulé discovered was the represents 2 electrons in a spin singlet. So these are the spins of the 2 electrons on the carbon, up, down, minus, down, up. I'm ignoring the spatial wave function here. And so each ellipse represents the entanglement of 2 electrons. And then the resonance that Kekulé discovered is the entanglement of 6 electrons. Okay, and so this particular theme of going from small number of entanglement to large entanglement is going to be a consistent theme in my presentation. Okay, so then quantum mechanics was discovered, and all of this, I think, with Kekulé's ideas, I'm guessing, were pretty well understood. And it seemed like you could have this peculiar thing of electrons doing this dance quantum mechanically and giving you a perfectly hexagonal shape. And so 1935, which is where most people would really talk about the onset of quantum entanglement, is where Einstein, Podolsky, and Rosen wrote this really fundamental paper, which started thinking more deeply about what quantum mechanics had implied. And they concluded that there must be something wrong. But of course, today we know there's nothing wrong. Some of the bizarre effects that they talked about are indeed present and now verified in numerous experiments. So what is the main point, and I'm paraphrasing here in modern language, that EPR said? Well, they said, well, just take the very simplest quantum entangled state. They didn't use the word entanglement anywhere in their paper. But anyway, take the very simplest configuration of 2 electrons which are entangled. For example, in a hydrogen molecule. So in a hydrogen molecule, you have 1 electron up and the other electron down, or vice versa, and the actual state is the superposition of these 2 states. But they said, well, imagine, so that's all fine for a hydrogen molecule, that's what quantum mechanics says. But imagine you could separate these 2 electrons without disturbing their spin. Then quantum mechanics would say that no matter how far you separated them, their spin would still be entangled. So one could be here, one could be in Boston, and if we just did it very carefully without disturbing their spin, they would still be in this superposition state. And so this led them to some rather bizarre, what they considered bizarre predictions, that if you were now to measure the spin in Boston and saw it was down, then quantum mechanics say that at that point, the wave function collapses and the other spin is up, or vice versa. So now you're getting something much more dramatic than just the structure of benzene. You're getting some highly non-local effect arising from the essential principles of quantum mechanics. And they argued that there's no way around this. In this, they were correct. And I think they speculated, well, eventually something will go wrong. And so far, nothing has, as far as we can tell. Okay. So, and this is sometimes called spooky action at a distance. I always wondered where that phrase came from. But I discovered Ahmed Almeri, a colleague, found this quote in a letter that Albert Einstein wrote to Max Born, which is in the library in Princeton. And there's this German word, which I won't try to pronounce, but that apparently means spooky action at a distance. So in fact, it was Einstein himself said that he cannot seriously believe in quantum mechanics because physics should represent a reality in time and space free from spooky actions at a distance. So why? So what's wrong? I mean, Einstein didn't like this action at a distance, and for good reason. There is no action at a distance, but there is an intrinsic non-locality, and the non-locality is not a violation of causation or relativity or anything like that. It's that the idea of a wave function is not local. That even when you separate these electrons, the local realism that philosophers like to talk about doesn't exist. The wave function, to the extent it's real, is neither here nor there. It's a property of the combined state. So once you accept that the wave function doesn't necessarily mean something, it doesn't associate with a given degree of freedom, it's a collective property of the entire system, then there's no problem with any causality or locality or anything. Anyway, okay. So of course, then in 2005, I think New York Times declared, yes, Einstein was wrong and spooky action is real. So this was an experiment not with electrons, but with photons. And of course, today now, 10 years later, this has been done many times over or much longer distances from the Earth to satellites and so on. And there's no question that you can actually observe precisely the effect that EPR discussed way back in 1935. Okay, so as I've already said, so this idea of philosophical question that EPR asked really put its finger on what was really novel about quantum mechanics. One, of course, was the principle of superposition, which people had understood. But now if you take the principle of superposition to more than one electron, two in their case, then many new phenomena can emerge. And that's playing a role in many things in physics today. Of course, most famously, in people trying to build quantum computers, I like to call them qubit devices. Well, anyway, we'll see where that leads, but this is not what I'm going to talk about. So in all of these devices, you're trying to control the entanglement of not just one or two electrons, but really of many different quantum degrees of freedom. And that's very hard to do because entanglement can be very fragile. It is very important that you decouple yourself from the environment. But I want to focus on quantum entanglement in nature, in particular multi-particle and long-range quantum entanglement. And what's become apparent in a lot of work that people have been doing condensed matter, including work by Youngbeck and Hae-Young and Arun here, is that this kind of long-range entanglement is very much needed to understand lots of interesting materials. And so I'll talk about my own favorite materials and how quantum entanglement is really the key to understanding its properties. There's another field where it goes back to a paper by Hawking in 1970 something. I'll have the date soon, which is Hawking's application of quantum mechanics to black holes. And this led to some very serious problems, somewhat analogous to the EPR paradox. But it seemed like there were some paradoxical properties of quantum mechanics near black holes. Today, I don't think anybody believes there's any paradox. And quantum entanglement, again, and particular multi-particle complex entanglement, has played a key role in resolving what was the problem when entanglement was not so well understood in the 1970s. Okay, so that's topic number one. So now I'm going to move on to a little bit more basic, just remind you of a few basic principles and how they apply of statistical mechanics. And then we'll come to the heroes of my story, which is superconductivity and black holes. So statistical mechanics, I date that to 1870. But before statistical mechanics, there was thermodynamics. And in particular, the second law of thermodynamics, which was discovered before, just as people studying engines, building engines, and trying to understand how heat and energy flow between bodies, before people even knew there were molecules existing or atoms existed. And so one important discovery of second thermodynamics was the concept of entropy, which is just some function that each macroscopic body had, which had to increase. And this is just a formal way of saying that there can be no perpetual motion machines, at least in real life, not on a TV cartoon. And temperature was also not something fundamental. It was just something you measured in degrees Fahrenheit or centigrade by having a liquid expand. So all of that changed in 1870 by Boltzmann, and his most fundamental contribution is on his gravestone in Vienna, which is entropy is kV log W. So now making a fundamental connection between a thermodynamic quantity and the microscopic constituents of matter. So W is a measurement in Boltzmann's language of the amount of disorder and the number of possible states a given system can acquire. So he was thinking certainly of dilute gases, like the gas in this room, made up of molecules of oxygen and nitrogen, and W was a measure of the phase space available to that gas. And so with this definition, a fundamental microscopic definition, Boltzmann showed you could go backwards and derive the laws of thermodynamics as having to do with probabilities of large systems, whereas previously they'd been discovered by empirical observation. And so the remarkable thing is that Boltzmann's result basically go through unchanged with the discovery of quantum mechanics, and you just replace W by the density of states. So you have some many-body system, you look at all its quantum states and just count them. So in fact, D of E becomes a much more precisely defined quantity than W. And then D of E is just the exponential of the entropy. And okay. All right, so the other amazing contribution by Boltzmann was 2 years later in the so-called Boltzmann equation. So here he started thinking about not just equilibrium thermodynamics, but time-dependent phenomena. And he wrote it in terms of this famous Boltzmann equation for the distribution function Fp of, say, particles with a certain momenta, classical dilute particles. So Fp is the number of particles per unit volume at a given position in space with momentum p. Okay, so the left-hand side is just a restatement of Newton's laws in this new set of variables. So nothing too profound there. But the profound contribution by Boltzmann was the term on the right. So this is looking at the rare collisions that happen in any classical gas, which are really important for the increase of entropy and it's to reach thermal equilibrium. But they happen rarely. And so this is the probability that two particles with momentum P and P1 collide. This is some scattering matrix element in quantum mechanics anyway, or the analog quantity in classical mechanics, T squared, some cross section, and they go out to momenta P2 and P3. Now, if you really were to write this down in full rigor, you would have to write down a two-particle distribution function on the right-hand side. So the key step by Boltzmann was the assumption that you could just write down the probability of two particles having momenta P and P1 as the product of the individual probabilities. And this is sometimes called the molecular chaos assumption, which means that once two particles collide, they just don't remember in a very short time when their previous collision happened. It's as if they were just already forgotten their previous collision. So once you make that assumption, you get this famous Boltzmann equation, which then was extremely successful in computing, for example, the viscosity of a liquid or a gas and so on, and giving you all kinds of interesting time-dependent phenomena. Okay, so now if you go to the modern era of electrons moving in a metal, the remarkable thing is that Boltzmann equation, again, survives basically unscathed, unchanged. So really the only thing that happens here, if you compare this equation and this equation, is these factors of 1 minus f. So this is for fermions. So the 1 minus f is just a statement of the exclusion principle, that if these two particles collide, the states they go into better be empty. And this is the reverse collision process. Of course, some short distance quantum mechanics will determine the collision cross section. Now, something bizarre happens here, which is really the key to understanding the behavior of metals, which is that because of these 1 minus f factors, collisions actually become very rare in a dense quantum gas. So classically, Boltzmann equation applies in a dilute classical gas. But in a dense quantum gas, it's only the small number of particles that are very close to the point between occupation and non-occupation, which is called the Fermi surface, that are important. And so this would, in fact, is the workhorse of solid-state physics in understanding how electrons, which are very quantum mechanical, behave, for example, in a metal like copper or silicon, or something like that. All right, so and so again, in this case, it's really thinking of this dense quantum system as made up of particles. Okay, the particles do, because of quantum effects, get a renormalization of their mass, and that's why I'm going to call them quasi-particles. But even in a very dense quantum gas, you can just think of it as and just use this Boltzmann trick. So this is really the foundation of almost everything in solid-state physics, apart from superconductivity. Everything follows from this. It's really quite amazing. Among other things, it can describe the flow of electrons in something like copper. And if you solve that equation carefully, you find that the typical time between scattering events of these quasi-particles diverges as temperature goes to 0. So this means the equation becomes better and better at lower and lower temperatures because this time becomes really long. And another consequence is the resistivity increases as temperature squared as you go down to 0 temperature. And this is, thoroughly confirmed, and many, you have to also put in phonons to fully understand what's happening in a metal. But anyway, those details I won't go into. So now you can ask the question, well, what is the fundamental bound to apply Boltzmann ideas of just quasi-particles moving around, which is, used in almost every paper you would find in solid-state physics before the 80s, without even stating it as an assumption. It's just assumed to be correct. Today, we know we have to be careful. And so we can ask now the question, when does this behavior fail? Well, it's going to fail when the time between collisions becomes too frequent. And you can use some argument like that and some kind of uncertainty argument to argue that this time tau better be bigger than what people are now calling the Planckian time, because it's the only time you make out of temperature and Planck's constant. So it better be bigger than this. And if it's not, then even the concept of a particle, which is independent of the others, or not entangled with the others, fails. Okay. All right, so that's it for a review of all of statistical mechanics and solid-state physics. And now we can now try to move into the 21st century. Okay, so superconductors. But before we do that, we go back to superconductors, and they were discovered in 1911 by Camaleonis, who cooled mercury down to a few degrees Kelvin. Anyway, okay. Or I'm told it was a student who discovered it, but he immediately took the student off the project. This is a joke, because either the student was wrong, in which case he had to be off, or the student was right, in which case he also had to be off. Okay, anyway, so that's in 1911. And then we fast forward to 1986, where, certainly my life changed. I was a young postdoc when this was happening, where this material, this class of materials, one of which is shown here, yttrium barium copper oxide, was discovered. So this is the very complicated chemical structure. Here's a little piece of it. And this goes superconducting at over 100 degrees Kelvin under the right conditions. So for example, if you take a little bit of this pellet of YBCO and dip it in liquid nitrogen and put it over just ordinary magnets, it's going to float around until it heats up and its temperature is above 80 Kelvin, and then there'll no longer be a superconductor. All right, so that's the first material and still the champion of high temperature superconductivity under ambient conditions, ambient pressure, and still something that's the focus of a lot of research. Okay, so I just mentioned this. So what good is this? Well, I would say the most exciting probable use is the use of high temperature, HTAs, is high temperature superconducting magnets. This is what Wall Street calls it, in fusion energy. So the purpose of fusion is to create strong magnetic fields in a very small area so that nuclei will fuse and produce energy. And so this company, and there are many other companies around the world, this is Commonwealth Fusion System. This is from their website. And they're trying to build, so this brown thing here are wires of YBCO. And these allow them to really operate these magnets at totally different conditions. And they have billions of dollars of startup capital. And so let's wish them luck. I'll certainly be very happy if any of this works. So that's why I want to work on YBCO. Well, not really, because it's theoretically very interesting, but it's great to have a potential significant impact. All right. So this is the phase diagram of YBCO as a function of electron density, which is changed in this case, by changing the oxygen concentration. And so you see this region here with the highest temperature superconductivity. And so we'd like to understand, what is TC? And of course, the big challenge here is, can it be even higher? Can you go all the way up to room temperature? Well, okay, nobody knows how to do that, but we're all hoping that'll happen someday. So to understand why this TC is so high, we have to ask what's going on up here before it became such a high temperature superconductor. And so, well, if you looked at this material down here where TC is not so high and it's not as exciting, you find a metal which has basically the same properties as copper. So there you think, okay, well, I just treat the system as copper and maybe I can understand why TCs, these lower TCs. But what about here? So that was one of the, again, a remarkable discovery. You seem to get a new phase of matter, sometimes called the strange metal, where the whole Boltzmann-Landau perspective completely fails. And so what are the things that fail? So many, many things, and that would take a more technical talk for me to go into it. But one of the most celebrated one is the temperature dependence of the resistivity. In copper, remember, I told you it has to be temperature squared. Here it's linear in temperature down to the critical temperature for superconductivity, and you can go even lower. And this is, this is quite a surprise and something that, we've been working on. And towards the end of my talk, if I time things right, I will tell you our current understanding of where the linear resistivity is coming from. But it's not just the resistivity. There's many ways of getting linear resistivity if you had phonons at very low energy. It's also what's called the optical conductivity. Here you're measuring, say, the reflectivity of a little piece of the superconductor as a function of frequency and temperature. And by analyzing this optical conductivity, you can read off this collision scattering time, tau, which is a function, the quantity that you would compute from Boltzmann's equation with the collision of quasi-particles. Here you're defining it in a way that if quasi-particles were present, if Boltzmann were right, this tau would be Boltzmann's time. Anyway, so you measure this tau of omega as a function of frequency and temperature, and it has this rather remarkable form, which is shown here. Its overall scale is exactly the Planckian time. So this tells us that the entire apparatus of Boltzmann equation has failed. It can't possibly apply. And the very existence of particles moving independently on their own and colliding rarely just doesn't work. So you really need, well, in a modern language, you really need to talk about a many-body system with true many-particle entanglement. And entanglement so strong that even the particles don't exist because they're all entangled with each other. All right, okay. So I'm going to try to address that problem fairly soon. So finally, let me take the story a different route again and tell you about black holes. Don't worry, I knew nothing about black holes until a few years ago. And even now I know nothing, but I'll tell you what little I know. Okay, so black holes. So black holes, another remarkable discovery where the theorists discovered it long before it was discovered experimentally. It was Carl Schwarzschild in 1916, who showed that the still young Einstein theory of gravitation or general relativity implied the existence of such objects, where if you took a mass m and compressed it smaller than this radius r, which is now called the Schwarzschild radius, then you would get a black hole, meaning that if the mass is in here, any light or any matter that may want to escape the black hole can never escape. The attraction of gravitation is so strong that everything inside the horizon is trapped forever. Lest you get worried about this, if you take an object, the Earth's mass, you have to compress the Earth to the size of a pea before the Earth becomes a black hole. So that seems highly unlikely. And so people were not too concerned about this strange solution of Einstein's equation. But today we know there are black holes everywhere. Here's the black hole with the Event Horizon Telescope at the center of the Milky Way. In fact, there is such a supermassive black hole at the center of every galaxy and many others, smaller ones elsewhere. This is so huge that it has 4.3 million solar masses, and its Schwarzschild radius is about the size of the Earth's orbit around the sun. So that's why it's called supermassive. Okay, so they exist and they were predicted theoretically. And so far, all experiments on black holes are in complete agreement with Einstein's theory. So now, we've already been impressed by how dense a black hole, but in fact, it's worse than that. In Einstein theory, once some matter collapses to a black hole, it doesn't stop, it keeps collapsing. So in Einstein's theory, you get a singularity. The matter, in fact, compresses to the center, and you have a matter of infinite density. So is that a real solution of matter as we know it? Well, it must be, because black holes exist now. But the singularity concerned many people and thought, well, this is just some unphysical solution of Einstein's equations. And after the invention of quantum mechanics, if something really became that dense, you couldn't teach it classically. You had to really apply a quantum theory of the collapsed matter. But there was no idea of how to do quantum mechanics in such a dense system with such strong gravity. Okay, so that kind of changed in 1975, where Hawking really gave the first description of a consistent interplay between quantum mechanics and gravity near a black hole. And I'll talk about his computation a bit later, but Einstein did a theory of the black hole, which very clever, not Einstein, sorry, Hawking. Theory of the black hole by just focusing on the outside of the horizon, thinking of the quantum mechanics at the horizon and outside, so that the whole difficult questions of what's really in the center could be sidestepped. And he concluded, and I'll explain that a bit later, that black holes have an entropy and a temperature. This is the temperature and the entropy, the famous Einstein-Hawking results, which are on his gravestone in Westminster Abbey, at least the first one. And also from Hawking's results, you can also ask about some kind of characteristic time for black hole dynamics. So in other words, suppose you had two black holes, they merge, and then they'll shake around, and eventually the black hole will become a perfect sphere while radiating some energy in gravitational waves. So there's some time it takes to become a perfect sphere. That's called the ring down time. And in Einstein's theory, if you work it out and you express the ring down time in terms of the Hawking temperature, it's again this beautiful Planckian time. So this is really the first hint. It was the first hint to me that there's some deep connection, or perhaps it's an accident. I hope to convince you it's not, between black holes and strange metals, because they both have this characteristic Planckian time describing their dynamics. Okay, so just to summarize, then now we have, this sets up a problem. There's of the gravestones. There's Boltzmann's result on his gravestone, S is equal K log D. Unfortunately, Hawking's entropy is not on his gravestone, but I put it in here. And so now the question is, how are these compatible? Boltzmann tells us the entropy has to do with density of quantum states, whereas Hawking tells us it has to do with just the area of the horizon. So where is this coming from? And are these two compatible? And that's really been a central question that many people in quantum gravity have been thinking about. And I'll give you some flavor of what we know today. In fact, the answer is yes, definitely they're compatible. And now we have some way of actually computing the value of D of E. All right, so that's the end of my introduction. How am I doing? Okay, about halfway through, right? Perfect. Any quick questions? All right, everyone's with me, right? Okay, now we're going to get more complicated. Yes, please. Well, you could say that, but the factor of 4 is due to Hawking. So Bekenstein didn't have everything. He had everything but the factor of 4. So it is his result in that sense. Yeah, area, Bekenstein's result of S is proportional to area. The other 3 you can deduce by dimensional analysis, but the 1/4 is definitely Hawking. Okay, so it's clear, hopefully I convince you that if you want to understand, well, I haven't quite convinced you of a black hole, but for superconductivity, we need to go beyond the EPR way of thinking and really think about entanglement of particles, not one at a time, but altogether, infinite numbers. And maybe that will help us understand superconductivity. That, at least that's what I was thinking way back in '93. I didn't know anything about black holes then. And so I'll talk about this model that Youngbeck mentioned. So, I told you that Kekulé came up with this model in a dream. So I decided I had to have a dream too. So there's this ancient Indian game of snakes that can go from anywhere to anywhere. And if you think of each snake as entanglement, which are rapidly moving around, well, that is what the SYK model is. So here's a more clearer description. So imagine there's a bunch of positions that some quantum particles, which are fermions, so they obey the exclusion principle, can occupy. So I've labeled them 1 to 19 or something. And so some of these are the particles, the purple objects. And so they're trapped in these positions. And now they're going to move around. They're going to tunnel from one point to the other. Now, typically, if you have such a situation in a real material, the electrons, this electron would hop there and so on. Well, if you did that, you very quickly realize that you'll end up with Boltzmann theory being valid at low energies. So let's prohibit that process. And we'll worry later about what's actually prohibiting it. But suppose there's a situation where the electrons can only move in pairs. So for example, there's a process, a tunneling event, where electron 11 and 12 will go to sites 5 and 14. And so in quantum mechanics, every such event is associated with a complex number, which I call U. All right, so that's one possible complex number, but there could be many other possibilities of these electrons tunneling in pairs. And each such possibility is order n to the fourth, as you can see, will have a complex number associated with it. So to understand what the electrons will do, I need to give you these list of complex numbers, and you got to put it into Schrodinger's equation and integrate it. And then you can predict the entire history of these electrons. I mean, I'm showing these events as happening sequentially, but they really all happen together. So they're really getting entangled by these processes. Okay, so you can go back and do that, but you'll quickly find that once you have more than 20, 30 electrons, this is too hard for even the best computer in the world. There's too many variables. Number of possibilities grows exponentially. And there's really no other method to solve this problem. So back in '93, I said, well, okay, let's make a simple assumption inspired by some earlier work in spin glass physics, that these complex numbers are independent random numbers. That's really the only assumption, that they don't have any special pattern. If you put your electrons in some generic position, they'll all have some set of value to get a table of these n to the fourth numbers, which specify the dynamics among 2 to the n states. So it's a very small amount of information to describe this huge space of possibilities. And let's just assume they're independent random numbers. And then we showed that, in fact, in the limit that the number of particles goes to infinity, you can now solve what's going on. You can figure out something about the state of the electrons, which are now strongly entangled, and compute many of its properties. Now, you might be worried that, well, all those properties will depend on exactly which list of numbers I gave you. In fact, they don't, even if you look at a single site, because everything is entangled with everything. Most of the properties are self-averaging. That is, you just need one sample, and this has now been tested numerically quite accurately, and you will understand and can predict successfully what's happening at any given site. It'll be this, it's just self-average for a single sample. And the reason it's self-average is because the number of quantum states is so gigantic. Even with 100 electrons, 2 to the 100 is, I don't know, more than the number of certainly molecules in the Milky Way. Okay. All right, so that's it. That's the SYK model. And you can solve it. And what you find in the end, you can prove, you get a state of matter in which if you were to deform it and try to move it around a little bit, you don't get Boltzmann picture completely breaks down. So here's kind of a toy model of many entangled particles. where if you wanted to set current flowing, it will not be carried by individual quasi-particles, but by really some quantum soup. Okay. And so here, for the more technically inclined, here's the actual description in second quantization. Here are the U alpha, beta, gamma, delta. These are the electron creation and annihilation operators. Q is the density of particles. And so this is the thing that can be solved in the large N limit. So the next 2 or 3 transparencies will be a little technical, but don't worry, I'll come back to more general discussion soon. So in the large N limit, what we showed is that you can get this, what I'm going to call G sub S, which is the n equals infinity or saddle point Green's function for any sample as n goes to infinity. It's just given by the solution of these 3 equations, where sigma is called the self-energy, and this is the Feynman diagram for it. And starting with this work and many other work since then, we know, actually only now, when I first wrote this down, I thought with my student Jean Voyer that, oh, somebody must have done this before. No, maybe it'll take us a few weeks to understand their properties. We're still understanding new things about these equations. And hiding in these very simple looking equations is some information on quantum gravity, as I'm going to show you. So one thing was shown fairly early on, especially in the work of Georges and Parcolet, that this lump of quantum matter that we have created has Planckian dynamics in appropriately defined tau of omega. It's of order h bar over kt with some function of h bar omega over kt. So that was very exciting. Although this is far, I wouldn't now rush out and apply this to the cuprate superconductors, because that's not what they look like. But we did speculate already in '93 that maybe some deformation of this is going to apply. And that's something I'm going to tell you about in a few minutes. Okay, how much time do I have? I have to end by 4:10, right? Or yeah, about 15 minutes. To the end. I started at 3:10. Oh, I thought I had a whole hour. Okay, well then. All right, I'm going to be quick here. So these equations have a certain symmetry. There's a time reparameterization symmetry, and there's a conformal symmetry. So this is for the experts. This just emerges from the system at low energies, and it's these symmetries that will then make the connection to black holes. Okay. one space. So it's one space in one time. It's something called JT gravity. And amazingly, if you take this JT gravity theory, you can further reduce it because of just by some gauge fixing tricks to theory in one time dimension. And this is the remarkable result that the theory you get in one time dimension for a charged black hole at low temperatures is exactly the theory you get from the SYK model. And the reason the two theories are exactly the same is because of fundamentally about the symmetry, because this symmetry of ADS2 is also the symmetry of the saddle point Green's function, as I flashed a bit ago. And furthermore, the emergent time reparameterization invariance is also present in gravity. I mean, in gravity that emerges for free, all of Einstein's equations are space-time reparameterization invariant. So here you just have a single time. So the net result is you can actually evaluate in the low temperature limit essentially the exact answer for a charged black hole. This is special for black holes with the net charge Q. Neutral black holes are, of course, the ones that are out there, and they're much harder. Nobody knows how to do that problem in general. But anyway, for a charged black hole, for example, for the SYK model, you have this result that comes from doing that path integral, the cinch square root of energy. And this is exponentially large prefactor showing these. This is the spectrum of the SYK model, but just by numerical diagonalization. It's an exponentially dense spectrum with chaotic states and no quasi-particles down to lower energy. And we believe charged black holes have exactly the same answer. You can actually get all these constants. And even the prefactor was obtained in some beautiful recent work by Ilyasu Murthy and Turiachi. So this is, the final answer that's come out from the SYK model of a realistic charged black hole in 3+1 space-time dimensions of the density of states, sort of resolving and really giving an answer that shows in the semi-classical limit not only Hawking's answer, but even corrections to Hawking answer. Okay, so this is the net result, that if you're looking outside the black hole, the SYK model is a good enough simulation of what the interior of the black hole is. I'm not saying that actually an SYK model is the center of a black hole, but it has the same basic properties. Probably to really understand what's inside a black hole, you need string theory. But these results, this entire result here, doesn't depend on any of those details. Okay, so I conclude by recapping. So these were the topics I've considered. And the main message is that there's a simple model of quantum entanglement that's making progress in understanding aspects of the high temperature superconductors. And if anything, has a bigger impact in modern studies of black holes, where not only the entropy and the density of states are now well understood for certain black holes, but also how quantum information escapes during Hawking radiation. All right, so to conclude, the SYK model describes multi-particle quantum entanglement resulting in the loss of identity of the particles. In one set of variables, this helped describe the strange electrical properties of YBCO. And a dual set, which are these time representation modes, it simulates, I wouldn't say it realizes, simulates the quantum degrees of freedom of charged black holes. Thank you.